Hi, it's Kate, and this is the first video for week 4 of Math 23B. So far, we've looked at double integrals, what they mean, how to set them up, how to compute them, and then we kind of put a pin in that discussion. And we started talking about determinants and their properties and how to compute those for n by n matrices. And just as I promised last week when I said, just wait, determinants are really, really important, this week is the moment where we put these two concepts together. So let's take a look. First, we're going to talk about a linear change of variable, and you might be wondering, why would we ever want to change variables? X and y seem totally fine to me, and that's great, except maybe the function that you're integrating is really, really messy if you integrate it in terms of x and y, or maybe the area of integration is really, really messy when you're looking at it as far as its relationship to the x-axis and the y-axis, and these are the two major jumping off points for when maybe you don't want to integrate in terms of rectangular or Cartesian coordinates x and y. Maybe you need to introduce a different coordinate system. Maybe you need to change your variables. So here we go, a linear change of variable. First, we're going to talk about t, and t is a linear transformation that is invertible. It maps from Rn to Rn, and our function f goes from Rn to R, and that's an integrable function. Assume that we are trying to integrate f over a particular region. Let's take a moment and see first that one of the things that t does, that invertible linear transformation, is that it takes the unit square and it maps it into a parallelogram, as illustrated in this beautiful diagram below. And so maybe the integral that we want to evaluate, now take a look below, we've sort of separated out that unit square and the parallelogram into two separate drawings. Maybe the integral that we want to evaluate is in what we call the original space. We want to take that function f and we want to integrate it over the parallelogram on the right. So we want to integrate it over this region right here. But of course, that's kind of a finicky area of integration to bound. Regardless of whether we're integrating by x first or by y first, there are going to be lots of different bounds as you're sort of slicing across this region, and so integrating over this parallelogram is a huge pain. It would be so much easier if we could just integrate instead over this unit square over here. And that's the key. There is a relationship between that unit square and that parallelogram. This nice square would be wonderful to integrate over because it's just a square. Its bounds are constant, and integrating with respect to constant bounds is just incredibly much computationally easier than integrating over a parallelogram where we have to keep changing the bounds again and again as we move across the region. And remember, that unit square on the left and that parallelogram on the right, they're connected to each other by that invertible linear transformation t. Now let's remind ourselves what t does. First, it takes both of the standard basis vectors and it maps them to the vectors that span the parallelogram. Let's draw that in. So there's a depiction of what t is doing to either of these standard basis vectors. And in fact, what t is really doing is it's taking a position vector for any particular point that's in the unit square on the left, and it's mapping it into a position vector for a point within this nice parallelogram on the right. And what's so great about this is that every point in the unit square can be mapped to another point in this nice parallelogram by t. The fact that t even exists is the tool that we're going to use. It means that it connects what we call original space to parameter space. So we actually can have our dreams come true. Like we said earlier, wouldn't it be so much nicer if all we had to do was integrate over the unit cube instead? Well, linear change of variable allows us to do just that. It exploits this mapping, t, that takes us from the parameter space to the original space. And by using this relationship, t, we're actually able to put our entire integrand, which originally was in terms of the original space, into terms with respect to the parameter space. There are a few different things that are changing as a result of this, but let's go over the concept. What we're doing is we're going to subdivide dyadically and evaluate Riemann sums in the original space, but the way we're going to do that is by summing over dyadic cubes in parameter space. For each dyadic parallelogram in the original space over here in the parallelogram, we're going to multiply the supremum or infimum of the function f composed of t by the area of the dyadic square in the parameter space. Realize what this is doing. T allows us to take a point in the parameter space and map it into a point in the original space. So using the function f composed of t allows us to take inputs in terms of the parameter space. Our entire goal was to put this integrand in terms of the parameter space, so that's how we manipulate the function. And then we also turn our eye to this term right here. This indicates infinitesimal increments dx dy in the original space, but of course in the parameter space it's going to be d whatever our new variable is and d whatever our new second variable is, and there's going to be a relationship there between the infinitesimal volume in the parameter space versus the infinitesimal volume in the original space. Since t maps from the parameter space to the original space, what we end up needing to do is multiply our entire integrand by the determinant of t, the absolute value of the determinant of t, because as you guys proved last week, the absolute value of the determinant of t is the volume stretching or scaling factor that's represented by the linear transformation t and how it affects the unit cube or unit square in this instance. The very last issue that needs to change are the bounds. Our bounds are no longer going to be in terms of our original variables. They will now be in terms of our new, what we call parameters. This is still the same process that we've been studying integration through this entire time. The key tool is to create a relationship or identify a relationship between the parameter space and the desired original space that's represented by this linear transformation t, and exploit all the amazing properties of t. The first is that we compose our new function with these new parameters. The second is that we take the determinant of t, which represents exactly what happens to volume under this linear transformation. And the last thing is that we convert our bounds to be in terms of our new parameters. At first, this can seem a little confusing without a few concrete examples to really clarify things for you. We're going to talk about how a general change of variables works. A linear change of variable is sort of a simplified version of this. And then we're going to take a look at various types of functions, as well as various regions of integration that really are ripe for using this change of variable. And that's going to be our focus for this week. So what does a general change of variables look like? Well, rather than necessarily having a linear parametrization function that maps parameter space into original space, we instead will have phi. Phi is going to be a more general, not always linear parametrization function. Usually, the variables that are first presented to you in the original space are x, y, and z, standard rectangular Cartesian coordinates. We're going to call those y1, y2 in our general change of variables formula. And then the generic names of variables in parameter space are usually u, v, and w. We're going to refer to those as x1, x2 in our succinct change of variables formula at the bottom of this page. So in practice, you'll be calling these x, y, z and u, v, w, depending on whether you're in the original space or parameter space. For us, we needed to make it a little more succinct and a little more easy to generalize. So at the bottom of this page, you'll see x denoting points in the parameter space and y denoting a point in terms of the original space. Now let's talk about a real practical example of when this is super useful. Okay, so say a problem is calling for you to integrate over a region that looks like this. It looks like about a quarter of a circle, but sandwiched between radius maybe 3 and radius 2 or something like that. Basically, this is a real pain to integrate with respect to Cartesian coordinates. And in fact, describing this region is not really that straightforward or that easy in terms of x and y as we know them, distance from the x and y axes on the Cartesian plane. And so what's a lot easier is to introduce a new coordinate system into the plane. And these are called polar coordinates. Most of you have probably seen them before, but for those of you who haven't or haven't seen them in a long time, let's take a moment and review what they mean. Now, here's a point in the plane, and the way we describe it in terms of Cartesian coordinates are that we denote perpendicular distance from the y-axis, which means along the x-axis, x, and then we denote it in terms of perpendicular distance from the x-axis, or in the direction of the y-axis, y. And so that's how we're able to specifically identify the location of any point in the plane according to this coordinate system. What do polar coordinates do? Well, rather than identify a point in terms of x and y, it identifies the point in terms of r, distance from the origin, and theta. Let's take a look at these two quantities. Now, r is pretty straightforward. Distance from the origin is quite intuitive. The only thing I really want to call out is that distance from the origin can only be positive. That's a rule that we use when dealing with polar coordinates so that we don't have a particular point identifiable by two different combinations of r and theta. And theta is found by looking at the angle created by a ray from the origin out to the point and the positive x-axis. Starting at the initial side along the positive x-axis and rotating in a counterclockwise direction, theta is the angle measure created by that initial side and that terminal side. So every point in the plane can likewise be denoted by a unique pairing of r and theta. And so we can find the conversion, the identities that relate x and y to r and theta. X itself, just using trigonometry here, is equal to r cosine theta. Y is equal to r sine theta, just from their relationship in this right triangle. That's where we get the parametrization associated with polar coordinates. And whenever you're given a parametrization, that's how you can identify the key components. This first component tells you how to calculate x in terms of this parametrization. The second component tells you how to calculate y in terms of the parametrization. So here's phi in terms of r and theta. Now, when we look down here and we compare this region in the original space and this region in the parameter space, it becomes clear how much nicer it is to use polar coordinates instead of Cartesian coordinates. We certainly need multiple integrals if we're going to stick with Cartesian coordinates, and the bounds are going to involve square roots at least once. Gross. Instead, what's great about this is that this region is easily described in parameter space by switching to how you would describe the bounds in terms of r and theta. R, distance from the origin, is constant along these lines. So perhaps this region is r is greater than or equal to 2 and less than or equal to 3. And then we realize that across this region, here's a line where r stays constant and theta changes. Theta is ranging from 0, this is clearly the positive x-axis, all the way to pi over 2. Both r and theta are bounded by constants, and so it would be so much nicer to do any sort of integration over this region in terms of r and theta, because in parameter space, if we're only discussing r and theta, our area or region of integration looks more like this, a nice plain rectangle over which we're going to integrate. So how does this work, you might ask? It's not exactly the same as before, where every little dyadic cube mapped into a tiny little parallelogram, but the same process tends to apply. We're going to subdivide the rectangle in parameter space dyadically, and the effect is basically going to be to divide the region in original space into smaller and smaller regions. What does this look like? These are my divisions in parameter space. Note that I've divided along constant r bounds 3 times and divided along constant theta bounds 3 times. And so I'm going to do the same thing in the original space. My art is not great, but each of those regions in the original space are bounded by 2 arcs and 2 radial lines. The issue, though, the point that I really want to point out is that if I kept dividing finer and finer and finer, Even though these regions are bounded by 2 arcs and 2 radial lines, when they get really, really small, they do look like parallelograms. And so when mapping a very small rectangle into a very small parallelogram, phi, which was originally a nonlinear function, is basically well approximated by a constant plus its derivative, d phi. So the appropriate stretching factor is going to be the determinant of the Jacobian of phi. Well, what does that look like in this particular case? There it is. And in fact, its determinant is just going to be r, which we calculate right down here. Now the only change is that the stretching factor is no longer a constant, and therefore must go under the integral sign. We cannot factor it out as we did in the linear change of variables case. But regardless, the rest of this is pretty much the same. In order for us to instead compute this integral in parameter space, where this very complicated region is represented by a nice rectangle, first, we compose the function with the parametrization, phi. Note that instead of everywhere we see an x, we'll plug in r cosine theta. Everywhere we see a y, we'll plug in r sine theta. Then we'll multiply by the determinant of d phi. That accounts for any stretching or scaling of volume. Last, instead of dealing with bounds in the original space, we're now going to deal with bounds in the parameter space, over here. So convert the bounds, convert the function, multiply by the volume stretching or scaling factor, and these two integrals are equivalent. Rather than forcing yourself to integrate over this awkward region in original space, we're now able to integrate with a few quick steps over a region much more straightforwardly defined in parameter space. This general change of variables formula, right here, is going to be your proof 17.1. It's not a particularly rigorous proof, but it's simply presenting an argument that walks through each of these conversion steps and why they work. You'll also be asked to explicitly work through the case where you're using a polar coordinates parametrization. Of course, this change of variable written in terms of polar coordinates shows first. Here's the function right here, written in terms of polar coordinates. Here's the determinant of the Jacobian matrix, r. We have dr, d theta out here, and then our bounds then are in terms of r and theta. That's the full transformation if we're moving into polar coordinates. Up next, we'll be taking a look at particular coordinate systems that come in handy in R3.